Acceptable connection methods for grounding electrodes to 1/2-inch reinforcement bar include exothermic welding, compression clamps, and bolted clamps. Exothermic welding is a permanent molecular bond formed by a chemical reaction between the conductor and the reinforcing bar. Compression clamps are listed devices that mechanically compress the conductor to the reinforcing bar. A bolted clamp is a listed device that utilizes bolts to securely hold the conductor to the reinforcing bar. Some trade names of listed compression clamps that are commonly used for grounding applications are Burn DYGG, which is a universal grounding connector for reinforcing bars, Airco Cadweld Exothermic Weld, which is a permanent grounding connection for reinforcing bars, Panduit GT12R, which is a grounding terminator for 1/2-inch reinforcement bars, Thomas & Betts G12, which is a compression grounding connector for 1/2-inch reinforcement bars, and Tyco FIT All, which is a universal grounding clamp for reinforcing bars. It is important to note that the specific type of connection method used must be listed and labeled for the intended application. Contractors should always refer to the manufacturer's instructions and local electrical codes for specific installation requirements and limitations. The National Electrical Code, or NEC, provides guidelines for safe electrical installations. Grounding is a critical aspect of electrical safety, ensuring that electrical systems have a path to safely dissipate fault currents. A grounding electrode system is a network of interconnected elements designed to provide a low impedance path to earth. The grounding electrode system can consist of various components, including ground rods, ground plates, underground metallic water pipes, and concrete-encased electrodes, often referred to as UFA grounds. Reinforcing bars, or rebar, encased in concrete foundations or footings can serve as effective grounding electrodes. The NEC specifies requirements for grounding electrode systems in Article 250. The connection of the grounding electrode conductor to the grounding electrode, such as a rebar, must be secure and provide a reliable, low-impedance path to ground. Several methods are considered acceptable for connecting to rebar. Firstly, exothermic welding is a process that creates a permanent molecular bond between the grounding conductor and the rebar. This method involves a chemical reaction that generates intense heat, fusing the conductor and rebar together. Exothermic welds provide a robust and corrosion-resistant connection, making them suitable for direct burial applications. Secondly, compression connectors are listed devices designed to mechanically crimp the grounding conductor onto the rebar. These connectors are typically made of copper or aluminum and are available in various sizes to accommodate different conductor and rebar sizes. Compression connectors must be installed using a listed crimping tool to ensure a proper and reliable connection. Thirdly, bolted clamps provide another acceptable method for connecting to rebar. These clamps utilize bolts to secure the grounding conductor to the rebar. Bolted clamps must be listed and made of corrosion-resistant materials. When selecting a bolted clamp, ensure that it is compatible with the size and type of grounding conductor and rebar being used. When installing grounding electrode connections, it is essential to follow the manufacturer's instructions and adhere to all applicable codes and standards. The NEC requires that all grounding connections be accessible unless they are buried or encased in concrete. Proper installation techniques are crucial for ensuring the long-term reliability and effectiveness of the grounding system. Regular inspections and maintenance of grounding connections can help identify and address potential problems before they lead to electrical hazards. The selection of appropriate connection methods and devices depends on various factors, including the size and type of grounding conductor and rebar, the environmental conditions, and the specific requirements of the electrical system. Consulting with a qualified electrical engineer or contractor can help ensure that the grounding system is properly designed and installed. It is important to understand the requirements outlined in the NEC and other applicable standards to ensure electrical safety and compliance. Grounding electrode connections play a vital role in protecting people and property from electrical hazards. By following industry best practices and adhering to code requirements, electrical professionals can create safe and reliable grounding systems. Additional considerations for grounding electrode connections to rebar include the following. Firstly, ensure the rebar is clean and free of any coatings or corrosion that could impede the connection. Wire brushing or grinding may be necessary to prepare the surface of the rebar before making the connection. Secondly, select a connection method that is compatible with the materials of the grounding conductor and the rebar to prevent galvanic corrosion. For example, using a copper connector on a galvanized rebar could lead to corrosion over time. Thirdly, when using compression connectors, ensure that the correct die size is used for the conductor and connector being installed. Using the wrong die size can result in an improper connection and compromise the integrity of the grounding system. Fourthly, when using bolted clamps, tighten the bolts to the manufacturer's specified torque to ensure a secure and reliable connection. Over-tightening the bolts can damage the clamp or the rebar, while under-tightening can result in a loose connection. Fifthly, protect grounding connections from physical damage and corrosion. This may involve encasing the connection in concrete or using a protective coating. Sixthly, document all grounding connections and keep records of inspections and maintenance activities. This information can be valuable for troubleshooting and ensuring the long-term reliability of the grounding system. Seventhly, consider the environmental conditions when selecting grounding connection methods and materials. In corrosive environments, such as coastal areas or industrial facilities, it is important to use corrosion-resistant materials and take extra precautions to protect the connections from corrosion. Eighthly, be aware of any local amendments to the NEC or other applicable codes that may affect grounding requirements. Local jurisdictions may have specific rules or regulations that must be followed. Ninthly, provide training to electrical personnel on proper grounding techniques and procedures. This will help ensure that grounding systems are installed and maintained correctly. Tenthly, regularly review and update grounding practices to stay current with changes in codes, standards, and technology. This will help ensure that grounding systems are always up to date and provide the best possible protection against electrical hazards. Proper grounding is essential for electrical safety and equipment protection. Grounding provides a low impedance path for fault currents to return to the source, allowing overcurrent protection devices to quickly clear the fault. A properly grounded system helps to minimize the risk of electric shock, fire, and equipment damage. The grounding electrode system is a critical component of the overall grounding system. The grounding electrode system provides a connection to earth, which helps to stabilize the voltage of the electrical system and provide a reference point for fault currents. The NEC specifies requirements for grounding electrode systems in Article 250. The grounding electrode system must be effective in providing a low impedance path to ground. The impedance of the grounding electrode system should be as low as possible to ensure that fault currents can flow quickly and easily back to the source. Several factors can affect the impedance of the grounding electrode system, including the type and size of the grounding electrodes, the soil resistivity, and the length and rarity of the grounding conductors. Ground rods are a common type of grounding electrode. Ground rods are typically made of copper or copper-clad steel and are driven into the earth. The NEC requires that ground rods be at least 8 feet in length and have a minimum diameter of 5/8 inch. Ground plates are another type of grounding electrode. Ground plates are typically made of copper or steel and are buried in the earth. The NEC requires that ground plates have a minimum surface area of 2 square feet. Underground metallic water pipes can also be used as grounding electrodes. The NEC requires that the water pipe be in direct contact with the earth for at least 10 feet. Concrete encased electrodes, or UFA grounds, are another type of grounding electrode. UFA grounds consist of a steel reinforcing bar encased in concrete. The NEC requires that the reinforcing bar be at least 20 feet in length and have a minimum diameter of 1/2 inch. The grounding electrode conductor connects the grounding electrode system to the electrical system. The grounding electrode conductor must be sized according to the requirements of the NEC. The grounding electrode conductor must be securely connected to the grounding electrode in the electrical system. The grounding electrode conductor must be protected from physical damage. The grounding electrode system should be inspected regularly to ensure that it is in good condition. The grounding electrode system should be tested periodically to verify that it is providing a low impedance path to ground. If the grounding electrode system is not functioning properly, it should be repaired or replaced. Proper grounding is essential for electrical safety and equipment protection. By following the requirements of the NEC and other applicable standards, electrical professionals can ensure that grounding systems are properly designed, installed, and maintained. Some additional points related to grounding electrode connections and the NEC include the following. The NEC Section 250.68 covers the requirements for connecting grounding electrodes. It specifies that the connection must be made in a manner that ensures a permanent and effective ground. The connection must be accessible unless it is buried or encased in concrete. The NEC Section 250.70 covers the methods of grounding electrode connection. It permits the use of listed connectors, exothermic welding, and other approved means. The NEC Section 250.53 A3 requires that all grounding electrodes that are present at each building or structure be bonded together to form a single grounding electrode system. This ensures that all parts of the electrical system are at the same ground potential. The NEC Section 250.64 covers the requirements for grounding electrode conductors. It specifies the size and installation requirements for these conductors. The grounding electrode conductor must be protected from physical damage and must be securely connected to the grounding electrode and the electrical system. The NEC Section 250.50 covers the requirements for grounding electrode systems. It specifies the types of grounding electrodes that are permitted and the requirements for their installation. The grounding electrode system must be effective in providing a low impedance path to ground. The NEC Section 250.52 covers the requirements for specific types of grounding electrodes, such as ground rods, ground plates, and underground metallic water pipes. It specifies the size and installation requirements for these electrodes. The NEC Section 250.166 covers the requirements for equipment grounding conductors. It specifies the size and installation requirements for these conductors. The equipment grounding conductor must be connected to the equipment grounding bus in the electrical panel and must be run with the circuit conductors. The NEC Section 250.118 covers the types of equipment grounding conductors that are permitted. It permits the use of wire, cable, and other approved means. The NEC Section 250.130 covers the requirements for grounding equipment connected by cord and plug. It specifies that the equipment grounding conductor must be connected to the grounding pin of the plug. The NEC Section 250.146 covers the requirements for grounding receptacles. It specifies that the receptacle must be grounded to the equipment grounding conductor. The NEC Section 250.148 covers the requirements for grounding lighting fixtures. It specifies that the lighting fixture must be grounded to the equipment grounding conductor. The NEC Section 250.106C covers the requirements for grounding motors. It specifies that the motor must be grounded to the equipment grounding conductor. Proper grounding is essential for electrical safety and equipment protection. By following the requirements of the NEC and other applicable standards, electrical professionals can ensure that grounding systems are properly designed, installed, and maintained. Always consult the latest edition of the NEC and local electrical codes for the most up-to-date requirements. It's also crucial to stay informed about any amendments or interpretations issued by local authorities. This ensures that all electrical work complies with the specific regulations in your area. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional advice. When in doubt, always consult with a qualified electrical engineer or contractor to ensure that your electrical system is safe and compliant. Staying current with industry best practices and code requirements is an ongoing process for electrical professionals. Participating in continuing education courses and attending industry events can help you stay informed about the latest developments in electrical safety and technology. By continuously learning and improving your skills, you can provide your clients with the highest level of service and ensure the safety of their electrical systems.